Okay, we're back. Example number 3. A hypercoaster is a special circuit roller coaster with a height measuring greater than 200 feet. If a new hypercoaster is under design to have its largest drop on the circuit modeled by the equation below, where d of t is measured in feet and time t is measured in seconds, find the average speed, velocity of the hypercoaster from 2 seconds to 8 seconds. Now remember, the key here is average speed. So we know that they're going to give us from one time period to another time period, because when it's average, we're going to have starting and ending. So what we're going to do is we're going to calculate our average rate of change, and it's going to be our change in d over change in t over that time period. That means we're going to have d of 8 minus d of 2 divided by 8 minus 2. So what I want you to do, since this is a calculator problem, they've given us that formula, we're going to go to our calculator. So go ahead and go get your calculator. I'm going to go to one on my iPad here, and we're going to go to y equals. We're going to hit y equals. This one is similar to the 84, and we're going to put that function in 1.87 and x caret 3, and then you have to arrow over, minus 20.64 x squared plus 112.79 x plus 132.56. My decimal point didn't go. 5, 6. Okay. So now I'm going to quit out of that. So second mode is quit. And I'm going to alpha y equals, basically giving myself a fraction. And then since I put it in y1, I'm going to go to vars. I'm going to go over to y vars, although what ended up happening here is it saved my, it saved what I did, so it took me straight to function, where I did not want it to do that. Vars, you should say over to y vars, number 1 for function, number 1 for y1. Okay, because you're wanting to put y1 in. It's already given me the y1. So let's try this again. Alpha, and then I've got my fraction bar, and we wanted vars, and again, I got y1 already, but it should have been vars, and then you arrow to the right to y vars on the top, and then you say number 1 for function, number 1 for y1. So we're going to do y1 of 8 minus, and again, we're going to do the vars and do the same thing, y1 of 2, and then divided by 8 minus 2. And so that's going to give us our 63.47. And so when we go back to our notes here, we get 63.47. And since this is a word problem, I'm going to go ahead and rewrite this as the average rate of change on the interval from 2 to 8, so t going from 2 to 8 seconds is about 63.47, and the height was in feet and the time was in seconds, so that would be 63.47 feet per second. Part B, what is the average speed? So again, we're paying attention to average speed, so it's going to have to give us a time frame. So we're doing the exact same thing. Please go ahead and pause the video and try to do that on your calculator, if you don't mind. And so for this one, it's going to be d of 6 minus d of 4 divided by 6 minus 4. And so if you go back this time, what I did was I put in my y1 of 6, and I got 470.18, and so this is going to be approximate, I think. And then I put in my y of 4, I got 373.16 divided by 2, and that gave me my 48.51. So there's different ways to do this, you know, just to whichever one you figure out works for you the best. And so now, again, since we have a word problem, we want to not only find our answer numerically, but then we want to explain that. So the average rate of change on the interval t values from 4 to 6 seconds is about 48.51 feet per second. So there's our explanation in words. Estimate the instantaneous speed. And notice that it's an estimate. Instantaneous speed at exactly 5 seconds. When they're asking for instantaneous, it's going to be an exact value, okay, at 5 seconds. But we know that right now all we can do, because we can't have division by 0, is say, well, I'm going to see what happens as I approach 5 seconds. So, here I'm going to let my 5 and 5.1 be my T1 and T2. And then how about 5 and 5.01? Now that second one is my T1 and T2. Right? So this would be my T1 and my T2. Now this one's going to be my T1 and my T2. Now this one's going to be my T1 and my T2. Notice your T2 minus T1 is 0.1 here. It's 0.01 here. It's 0.001 here. So that is getting closer and closer and closer to, basically to having it 0, but it's not going to ever be exactly 0. So go ahead and pause the video, and you should be calculating your d of 5.1 minus your d of 5 divided by 5.1 minus 5, and tell me what you get. And then the same for the second one, d of 5.01 minus d of 5 divided by 5.01 minus 5, and then d of 5.001 minus d of 5 divided by 5.001 minus 5. And when you come back, let's go ahead and hopefully you went away and got your answers to be close to mine here. That one was my first one. This was my second one. This one was my third one. Since you are getting closer and closer and closer to 5, like you're 0.1 second away, you're 0.01 seconds away, you're 0.001 seconds away, you're getting closer and closer and closer. This one is going to be what it, is the one that it's approaching. You can see that as you go, it was 47.4, 46.7, 46.6, right? So getting closer and closer and closer. So I would estimate that the instantaneous speed, I should say at 5 seconds, is about 46.647 feet per second. Remember, you want to take it 3 places behind the decimal point for the AP exam. This 4 told me to leave that 7 alone. And this was basically, since it was a word problem, we were rewriting what our conclusion was that they had asked us for, just like we did above. And now part D, explain the meaning of the instantaneous speed in the context of the question. So they want you to talk about the problem that we've been working about, the hypercoaster. So we're going to say that the rate of change, because that speed is a rate of change, in the drop of the hypercoaster at t equals 5 seconds is about 46.647 feet per second. Okay. So now let's go to that last example. This is example number 4, airport departures. The traffic pattern of departing flights at Orlando International Airport on a fall afternoon can be modeled by the function v, defined by v of t equals 92 minus 15 sine of t over 3, where v of t is measured in vehicles and t is measured in minutes between 0 and 30. Find v of t for t equals 18. So that very first one, v of 18, is going to be 92 minus 15 times the sine of, and we've got 18 divided by 3 here. So 92 minus 15 times the sine of 6. So that one is easy to put in your calculator, but what I would like to do is put this into the graphing calculator. Y equals, we'll go up here, clear, 92 minus 15 sine. And then I'm going to do a fraction there. And when I go out, I could do my y1 of 18. And we'll get approximately 96.191. So we'll go back. We'll say approximately 96.191. And so this would be vehicles, right? Because our V is measured in vehicles. V of t is measured in vehicles. This is, so about 96 vehicles at time 18 minutes is what you're going to see based on this function. So now, part B, make a sketch of the graph of time versus number of vehicles and be sure your graph has a scale. So for this one, we know that if t is 0, the sine of 0 is 0, and so we know at 0 here, we're going to have, let's just put it about right here, 92 vehicles, okay? Now, when your sine is at its highest, it will be 1, right? Highest is 1, lowest is -1. So if this sine of whatever became 1, that's going to be 92 minus 15. And so that's going to be 77. So it's the lowest it's going to go is 77. And then if it were -1, that would end up being 92 plus 15. So the highest it's going to go is 107. And like I said, we know that this point is here. And if we go to our calculator, hopefully you guys had that in your calculator and you were looking at it. If I want to look at the graph and I want to look at it just between 0 and 30 so that I can see, do you see how it goes down and then back up and then down, and it ends at 30. It looks like it ends right at 100, or well, yeah, right at about 100 at 30. So let's go ahead and try and sketch that. So it goes down and then up and then down, and at 30 it's about at 100. Okay, so let's just extend this and pretend like that was 100 and this right here is 30, because we really only care about from 0 to 30, and again that was time in minutes. We want to mark that, and this is number of vehicles. Ooh, I just looked at my graph and decided that it was not very pretty. I went kind of over here. Oops. Now I erased the whole thing. Okay, so down, up, down, up, and maybe about right there is our 30 now. Okay, so that looks a little bit better. Part C, what is the average rate of change of the vehicles at the departing flights over the time interval from t equals 15 to t equals 20? So again, paying close attention, average rate of change, and it gave us a starting and an ending time. So that was our hint that we're going to be calculating that v of 20 minus v of 15 divided by 20 minus 15, and that is our average rate of change. So go ahead and pause your video and calculate this for me. I'm going to go to my calculator and calculate it also, since we have darn it. Since we have our y1 of 20, 86.387 minus our y1 of 15, 106.384 divided by 5. So we've got our 86.387 minus 106.384 divided by 5. That's like, I guess we could put negative 3.999, but it's like 4. So this is about approximately negative 3.999 or negative 4. Now, the units per minute would be vehicles per minute. That means the number of vehicles, I put an H instead of an L, vehicles per minute. That means that during this time frame, the number of vehicles is reducing, right? That's what that negative is. So now, D, estimate the instantaneous rate of change of vehicles at t equals 18 by finding the average rates from t equals 18 to t equals 18.1. t equals 18 to t equals 18.01, and t equals 18 to t equals 18.001. So again, this is like our, like our T1 and our T2. And what we're doing is we're getting closer and closer and closer so that our T2 minus T1 is getting smaller and smaller and smaller, that is approaching zero, because we really want the instantaneous rate of change at t equals 18. But the only way we can do it right now is by just looking at it as it approaches zero, okay? So this is going to be our v of 18.1 minus our v of 18 divided by 0.1, our v of 18.01 minus v of 18 divided by 0.01, our v of 18.001 minus v of 18 divided by 0.001. Do you see how I just went ahead and said that my T2 minus my T1 at the bottom was that? And so now we want to go and put these values in and get that calculation so that you can see. And I want to go ahead and start with a fraction, and I'll be my y1 of 18.1 minus my y1, oops, sorry, well, this thing's not working great for me. Sorry guys, I accidentally hit Y2 there. I had to go back, correct myself. We all make mistakes. So our first one's negative 4.823. So let's go negative 4.823. Our next one, I'm going to go ahead and do that and then make that an O. And I do want to insert, so I'm going to go like that. 1. And then here, it's going to be an insert O1, negative 4.803. And we're going to insert another 0 there. And we're going to insert another 0 there. Oh, it didn't do it on that one. Okay. And negative 4.801. So you can see it's getting closer and closer and closer as you go down to just negative 4.8. So I would say that our instantaneous rate of change in traffic flow I almost said from, at t equals 18 seconds is about negative 4.8 vehicles per minute. And it says, why can't the instantaneous rate of change of traffic in the departure lane with respect to time be calculated using the method in Part D? And we said that if we did it at 18 and at 18, we would get division by 0. So it's because we would end up with division by 0. So instantaneous at 18, mathematically using average velocity does not work because you don't have a beginning and an ending time. You need a beginning and an ending time. So what we do to estimate it is we make it a really, really short time interval around 18. And of course that negative means it's decreasing. So that traffic flow is slowing down. So I could say, or the instantaneous rate of change of traffic flow is slowing down at t equals 18 seconds at a rate of about 4.8 vehicles per minute. So that's another way to say that. Instead of just using the negative 4.8, you could say that it's slowing down at a rate of 4.8. So that slowing down piece would take the place of this negative sign. Okay? All right, that's